Hello dear students, I am Chaman Kumar from JNBKY West Tripura. I welcome you all once again to my class. Okay, in the last class we had discussed the definition of conservative force and its different properties. In this video we will discuss the principle of conservation of mechanical energy. Okay, so in the last class we had one property of the conservative force. Okay, the last property, what it was, uh, if in a system only conservative forces are acting, okay, the total mechanical energy will be conserved. So okay, this is what we have studied in the last class. Okay, so we'll get deep into that. So before we get into that, let me explain what do we mean by mechanical energy. All right, so generally a system has two kinds of energy. All right, if it is moving, it will possess some kind of kinetic energy. If it is at rest, then it will have some uh, potential energy. All right, and sometimes it also has both kinds of energy, potential energy as well as kinetic energy if it is at some height from the ground. All right, so if only conservative forces are acting to the system, then the sum total of these two energies, like kinetic energy and potential energy, these two energies, the sum of these two energies will be a constant. Okay, conservation means their value will not change, it will remain fixed, conserved. Okay, so let's go into the slides and understand it deeply. All right, so here comes the first slide. All right, so here in this slide we will discuss the principle of conservation of mechanical energy. All right, the definition goes like this: the principle of conservation of mechanical energy states that if only conservative forces are acting on a system, then the total mechanical energy, that is kinetic energy plus potential energy, is constant. Okay, so this is the statement of the principle of conservation of energy. All right, now in this slide I will prove also this. All right, so here is the proof. All right, so to prove this, what we have to do, let's take a body. All right, let's take a body which undergoes a displacement delta x, okay, under the action of a conservative force f of x. So this is the amount of conservative force. Okay, this is the conservative force that acts on the body, and this is the displacement that the body undergoes under the action of this conservative force. All right, so according to the work energy theorem, what does the work energy theorem say? The change in kinetic energy is equal to the amount of work done on the body. All right, this is from the work energy theorem. In the previous unit we have studied. All right, so delta K is equal to f of x into delta x. The change in kinetic energy is equal to the amount of work done by the force. All right, and if the force is conservative, the change in potential energy is equal to the negative of the work done. This is also a property of conservative force. All right, so this the first point, delta K is equal to f of x into delta x. This comes from the work energy theorem, and in the last unit we have studied. All right, and this one, okay, delta U stands for the change in potential energy, and this is the negative of work done. All right, this is the negative of work done as we have studied in the conservative force. So this is equal to negative of delta K. From these two, these two equations, we can get that the change in potential energy is equal to the negative of change in the kinetic energy. If I will bring this kinetic energy to the left side, delta K plus delta U will be 0. All right, or the change in kinetic and potential energy equal to 0. Okay, if the change in 0 means the value is obviously constant, or the kinetic energy plus potential energy is constant, or we can also express it like this, that total kinetic energy plus potential energy in the initial condition is equal to the total kinetic and potential energy after you know in the final situation. All right, initially and finally the sum of the kinetic and potential energy is constant, the total mechanical energy is conserved. Okay, this is how we prove this. What does it mean? It means that the sum of the two energies is constant, but individually they may change. Okay, one may be more, one may be less, but the total, the sum of these two values will be constant. So this is what the principle of conservation of mechanical energy is. All right. Now we will prove this by taking an example. All right. Here it comes. So here what we have done is, all right, here we will prove this conservation of mechanical energy in a freely falling body. Okay, we will mathematically prove it, okay, with an example. All right, so here is the proof. All right, so see the diagram carefully, what we have done. So here is a body of mass m, all right, and it is falling down. All right, okay, it is falling down. So at different positions it is falling down means what kind of conservative force act on this body? That conservative force is your gravitational force, and gravitational force is a conservative force that acts on this body, right? So we will take three positions: position A, position B, and position C. All right, so these three positions we have taken, and we will mathematically prove that at all these positions the mechanical energy is conserved, the total mechanical energy is conserved. All right, so let's check one by one. Okay, so we have considered a body of mass m, all right, which is falling from a height of h. Okay, this is the total height h under the action of the gravity, which is a conservative force. We shall consider 3 points A, B, and C. So at all the 3 points, we will find out both the energies, kinetic and potential, and we'll add them at each point. All right, this is our tactic. So first of all, we'll consider point A. All right, the total point A, the kinetic energy of the body is how much? As at the topmost point, the body is initially at rest, so kinetic energy will be 0 because the no velocity. Okay, so kinetic energy at the position A is 0. Potential energy of the body at the highest point will be how much? Mg into height of the body. What is the height here? At the position A, the height is h, so mgh. So what will be the total energy? Okay, kinetic plus potential, it is mgs, and this is equation 1, mgh. Remember this value. All right, so to prove the conservation of mechanical energy, what we have to do? We have to prove that at the next 2 points, means B and C, the total energy should be equal to mgh. As mgh is the total energy of the first point, the second 2 points also should have the same amount of energy. Okay, now check at the point B. All right, at the point B, the velocity of the body will be, let B. All right, BB is the velocity of the body. So we have to find out first the velocity of the body. All right, and by using the third equation of motion, we can get it that, okay, b square, this is the final velocity at B. All right, and initially the velocity was 0, so b square minus 0 square is equal to 2gx. Okay, so kinetic energy will be how much? Half into mbb square is equal to half of m into 2gx. Instead of bb square, we have put 2gx, so it will be mgx. So this is the amount of kinetic energy. All right, and let this much of height is h minus x. We have taken from A to B, the distance is x, so this much of height is how much? H minus x. So the potential energy at the point B will be how much? Mg into h minus x. So on adding these two, we will again get mgh. All right, so at the point A, the total mechanical energy was mgh, and at the point B also the total mechanical energy is mgh. Now one more point left, which is point C. Let's see what happens here. At point C, let the velocity is bc. All right, so bc square minus 0 square will be 2gh. All right, so vc square will be 2gh, and kinetic energy will be again mgh. And at the bottom, at the bottom the height is 0, so potential energy is also 0, and the total mechanical energy will again becomes how much? mgh. So at all these points A, B, and C, the total mechanical energy is how much? mgh. But individually the potential and kinetic energies are changing. At some point they are increasing, at some point they are decreasing. We will see in the next graph what happens to their individual values, but together they are making the same value mgh at all the points. So we have seen in this slide the conservation of mechanical energy in a freely falling body. All right, so here is the graph showing the variation of potential and kinetic energies during the process of this falling. All right, so the graphical representation of the variations of kinetic and potential energy from the graph. Okay, see the graph. So what is the graph about? This graph shows in the x-axis we have taken height of the body at different heights, and in the y-axis we have taken energy. Okay, it may be potential or kinetic. All right, so we will see first of all the variation of kinetic energy. All right, so we'll see at the variation of kinetic energy. So this one is for kinetic energy. Okay, now see that. Okay, we can see that h equal to 0 means it is point C. H equal to 0 means it is point C, like this, point C, at point C, h equal to 0. All right, so h equal to 0, so potential energy is 0 here. Look at this potential energy graph, it starts from 0, so potential energy is 0. Why 0? Because the body is at ground. All right, and see the kinetic energy. Okay, on reaching the ground, the kinetic energy becomes maximum. All right, it touches the ground with the highest velocity, so the kinetic energy will be maximum. Okay, at the ground, when it reaches the ground, the potential energy is 0, but kinetic energy is maximum. And see at the highest point, this one is point A. All right, when the height is s, the point is A. What happens here? The total kinetic energy is 0. Why 0? Because the body is at rest. Because the body started falling from that point, so kinetic energy is 0, and at this point the potential energy was highest. All right, and all the points in between, there are the body has both kinetic and potential energies. So as the height increases, the potential energy gradually increases, but what happens to the kinetic energy? The kinetic energy gradually decreases, and this line is the total energy. Okay, this line is the total energy. Okay, at each point the total energy is constant. Okay, no matter what the point is, A, B or C, the total energy is constant, but individually they are varying. How they vary? The kinetic energy decreases with height while the potential energy increases with height. So this is an interesting graph. All right, so in this video we saw that how the mechanical energy remains conserved when only the conservative force is acting on a system. Okay, we have proved this, uh, proved this by considering the properties of conservative force. We have also proved this by using a freely falling body. Okay, so this is what the law of conservation of mechanical energy says. Okay, in the next video we will see what do we mean by collision and how many types of collision are there, and we'll see 1 and 2 dimensional collisions. Okay, thank you.